Okay, so this video works through a practice quiz 7. And so in this first problem, we have an electric current that's described to us, and we have to calculate the size of the electric current. So the units for electric current are the ampere, a symbol of an uppercase A, and all it is coulombs per second. So pretty simple. So electric current, we can actually just figure out the formula from the units, can't we? Is equal to charge, which is measured in coulombs, over time. And as 1 ampere is equal to 1 coulomb per second. So pretty straightforward. You've just got to get all of our units correct. So we've got 290 coulombs, 290 microcoulombs. So micro means times 10 to the minus 6 coulombs, and that is being transferred in 416 milliseconds, and milli is just 10 to the minus 3, and so that would give us coulombs per second, or alternatively that would give us amperes, and then we just got to get our 3 sig figs. So let's give that a go. 290 micro coulombs divided by 416 milliseconds. Looks good. And so to 3 significant figures, we've got 6.97 times 10 to the minus 4 coulombs per second, or 6.97 by 10 to the minus 4 amperes. And amperes, because it's named after Professor Ampere, it has an uppercase A for its symbol. Okay, this one looks like we're going to be relating delta G naught, K, and E naught. So how are these guys related? So delta G naught equals minus RT log K. We also know that delta G naught equals minus NF E naught. So that should do it, right? That's it. So if you want to get fancy, you could say that NF E naught is equal to RT log K. But I mean, that's just really combining those two first equations, isn't it? Alright, so something to keep in mind, for a spontaneous reaction, delta G naught should be less than 0, K will be bigger than 1, and E naught will be greater than 0. So that helps us with checking for consistency. And again, if delta G naught is greater than 0, that means we have a non-spontaneous reaction. So K we would expect will be less than 1, and E naught will be less than 0. So we can always kind of check consistency there. N relates to the moles of electrons being transferred. So we need to know how many electrons are being transferred in our redox process. R is the ideal gas constant, T is the temperature in Kelvin, and one thing to be aware of is that we need to use SI units for these things. Delta G needs to be in joules per mole, but it's often going to be given to you in kilojoules, so keep an eye on that. Alright, let's have a look here. So it says a student made measurements on some electrochemical cells and calculated 3 quantities, delta G, K, and the cell potential. His results are listed below. Unfortunately, the student may have made some mistakes. Examine his results carefully and tick the box next to the incorrect quantity in each row, if any. So the important thing that we're going to do is we're going to check for like logical sense. So delta G should have the opposite sign of K and E. Alright, so that's what these two things are really telling us here. So let's see what we've got here. So delta G is negative, so K and E should be positive. And what we see is that that is inconsistent, right? So that guy there is not right, okay? So it says if there is a mistake in a row, only one of the three quantities listed is wrong. So be aware of that. Okay, so delta G in this second one is a negative. So K should be bigger than 1 and E naught should be positive. So K in this case is really, really tiny. So it must mean that K is incorrect. In the final one, delta G is positive. So we would expect a small k less than 1 and a positive E naught. And what we find is that we have a really positive k, but we do have delta G is positive, so we will expect a really small k and a negative E naught because this is describing a non-spontaneous process. And so we see that the delta G and the E naught are consistent. E naught is negative, but the k is a big number, so the k must be wrong. Okay, k needs to be a small number in that case. So maybe they got those two numbers flipped. That would be a very easy mistake to make, wouldn't it? Okay, cool. All right, easy going. Okay, we don't have to calculate anything in this case, so no need to use the formulas. Use the standard reduction potentials from the ALEX data table. Calculate the standard reaction free energy delta G for the following redox reaction. Round your answers to 3 significant digits. So the first thing to remember is that the cell potential is equal to E naught cat minus E naught anode. And then to get delta G, we're going to use our little formula, delta G equals minus NFE naught for the cell potential. So it's going to be a two-step process, right? So in order to do this, we're going to need to find the standard reduction potential for our cathode reaction and then subtract from that the standard reduction potential for our anode reaction. So what is being oxidized? What is being reduced? So I like to look at the elements, right? If I have something that's an element in here, then I know that that is going to be oxidized or reduced. So this is in its elemental form, so the oxidation number is 0. And then chlorine over here is in the ionic form, and our rules for oxidation number tell us that that the charge on a monatomic ion is just equal to the oxidation number. So chlorine, its oxidation number went from 0 to -1. This is my reduction. Or we can say it's my cathode reaction, right? It's my cathode reaction. So one thing just to be aware of is that this is taking place in under basic conditions. So when I look that up, if there's an option for basic conditions, I need to pick that one, not the one for acidic conditions. So let's see, do we have this reaction? That's going to be my cathode. That's the standard reduction potential that I got to look up there, right? So I'll have to look that guy up. Now that must mean that my oxidation involves, the hydroxide ions are really just describing the conditions, right? That it's under basic conditions. My oxidation must be this reactant here. So manganese in here, my rule is, so we've got 1 manganese and then we got 2 oxygens, and this is oxygen is -2 in most compounds. That has to add up to 0. So manganese must be +4 here. And then when I go over to here, you can see I've got MnO4. It's got to add up to -1 in this case. So X for the manganese, 4 lots of oxygen. And they're going to be -2 because oxygen is -2 oxidation number in most compounds, and that's got to add up to -1 in this case. So X minus 8 equals -1. So X must be equal to, you guessed it, +7, right? So it goes from +4 to +7 for the manganese there. So it got oxidized, right? Got oxidized by 3 electrons, right? +4 to +7. So this is my oxidation reaction. Is these guys. Got to be good at doing your oxidation numbers to get that. So that's my oxidation, and oxidation occurs at my anode. Okay. All right, so my oxidation reaction, remember you want to write it reverse because the tables list reduction potentials. It's going to be MnO4 minus going to MnO2, and that is going to be my anode reaction. So let's look these guys up. Go to the Alex data section, look up standard reduction potentials, and we need chlorine being reduced to chloride. Now we've got standard reduction potentials, there they are. They're kind of in alphabetical order. Here is our first one. Make sure we get the conditions right. Is it chlorine gas going to chloride? 1.358. It was chlorine gas, so that was 1.358 volts. And then for the manganese, this was a solid and this is AQ. You just want to get the phase right, and remember it's in basic conditions. So MnO4 minus. MnO4 minus, that's in acidic conditions. We don't want that one. We want this one, basic conditions, 0.595. Aqueous, solid, that's it, 0.595. See how I didn't change the sign? So then our cell potential is the cathode minus the anode, 1.358 minus 0.595, units there being volts, 1.358 minus 0.595 equals that, 0.763 volts. So that is my cell potential. Now that's just the first part of the problem, right? Because what we need to do now is to put that into our little formula and to get the actual delta G for this reaction. And they want units in kilojoules, so we'll have to do a bit of work there to get that as well. So the next thing that we need to figure out is what is the number of electrons transferred. Now if we look in our balanced equation, we can see that 3 chlorines get turned into 6 chlorides, and that's going to be this reaction up here times 3, isn't it? So instead of it being 2 electrons, it's got to be 6 electrons. And that's the number that we needed. We needed to figure out how many electrons are being transferred. So N equals 6. Now you can look at any of your 2 redox reactions to figure that out. I just figured that it was easier to look at the chlorine there. So, because remember, electrons lost equals electron gained, so it doesn't matter what one of the pair you look at. So delta G naught equals minus NF E naught cell, and that's going to give me my answer in joules, right? So there we go. So we got minus 6 times, and then F is Faraday's constant, 96,485. And then E naught cell, well, we just calculated that, didn't we? 0.763. And as I said, this is going to give it to you in joules. And we're probably going to divide that by 1,000 and get it into kilojoules, right? Depending on how that looks. So minus 6 times F, 96485, times E naught, 0.763, equals negative 441708 joules. And if we divide it by 1,000, we'll get our answer in kilojoules, minus 442 kilojoules. Now, what do we know about spontaneous reactions? If delta G is negative, that means it's spontaneous. And then E naught cell should be positive, which in this case we have a positive E naught, 0.763, and we have a negative delta G, so I know that I got this right. So minus 442 kilojoules for this guy. And everything seems consistent. All right, so identify the cathode and the anode. Look up the values for the standard cell potentials or standard reduction potentials for those anode and cathode electrodes. Then you'll need to identify the number of electrons that is being transferred once you've got the cell potential, and then you can plug that into that final formula. And at the very end, you always want to check for consistency. If I've got a positive cell potential, I want a negative delta G, and vice versa. All right, let's have a look at this one. In the industrial chlor-alkali process, pure chlorine and sodium hydroxide are produced. Okay, so we're going to make CO2 gas and sodium chloride. And we're going to do this by electrolyzing brine. So brine is salty water, so that will be an aqueous solution. Right? Oh, sodium hydroxide, not sodium chloride. Terrible. Sodium hydroxide. Okay, so it looks like we're going to have something like this. Brine is salty water. And then we're going to run some electricity through it, and we're going to make, well, we can balance this if we need to. I'm going to make these guys, 2 of those. How's that look? Close. Feel like we've got an extra oxygen here. And there must be another product. Otherwise, this isn't going to work out. And I think that other product is hydrogen gas from memory. So if we do that, we would need 2 of those. And then I believe that this makes hydrogen gas. We could look that up if we wanted to, but it isn't actually that important. So it says suppose a current of 950 amperes. So that is 950 coulombs for 1 second is passed through an aqueous solution of sodium chloride for 50 seconds. So 50 seconds. Calculate the mass of pure chlorine produced. Oh, interesting. Okay. So what I think is important here is to think about what we've got to do to get the chlorine, right? So the chlorine is coming from the sodium chloride, and what we see is the sodium chloride, it's an aqueous solution, is we have 2 chloride ions get oxidized to produce 1 CO2, right? That's what's happening with the chlorine. So what we know is we've got coulombs here. We know that we get 1 mole of electrons for every 96,485 coulombs. That's Faraday's constant. And then from this balanced equation for the oxidation of a chloride, we know that we get 1 mole of CO2 for every 2 mole of electrons that pass. So that will give us our moles of chlorine. Now, we're asked to calculate mass, so we'll have to use the molar mass of chlorine here. So for every 1 mole of CO2, I'll just quickly put that together, we get 70.90 grams of CO2. There we go. So the time and the current told us the number of coulombs that were passed. We then used Faraday's constant to convert that to moles of electrons. And then finally, we realized that for every mole of chlorine that is produced, we have to pass 2 moles of electrons. So we could use that mole ratio to calculate the mass of chlorine gas produced. And then finally, the moles of chlorine gas, and then finally we use the molar mass to get there. Now, it's all a big dimensional analysis problem, really, right? And then we'll check our units, and sure enough, we get what we wanted, which is grams of chlorine remaining. So that's it. We just kind of had to reason our way through this, right, rather than anything else. So that's it. Okay. I just wanted to move this over so that you could see what we've got here. Okay, so it was 950 coulombs is what I was trying to show you. Okay, so 950 coulombs per second times 50 seconds times 1 mole of electrons for every 96,485 coulombs, that's just Faraday's constant, times 1 mole of chlorine is produced for every 2 moles of electrons that moves, times, and it's 70.9, well, we should check the exact molar mass. I just did that in my head, but .91, I would have been out by 0.01 grams of chlorine for every 1 mole. There we go. So this ends up being 17.45 grams of chlorine, not O2, chlorine that is produced, and then you just have to round that to the correct number of significant figures. Okay. All right, that wasn't too bad. It's just really dimensional analysis. I think the difficult part is recognizing that the reduction of chlorine requires 2 moles of electrons because chlorine is a diatomic element. Okay. All right. So we have this redox reaction here. And so, okay, so what they're describing is a cell where we have non-standard conditions. So instead of all of the solutions being having concentrations of 1 mole per liter, they are all much greater than that. And in particular, we can see that the tin concentration is significantly greater than the barium concentration. So what I'm thinking is that this is going to push it towards products more. So it's going to have a greater cell potential than the standard cell potential. So how do we calculate that? Well, the cell potential under non-standard conditions is given by the Nernst equation. So it's E0 cell minus RT on NF log Q. Okay, so let's turn that off because it keeps correcting it. So Q in this case is the reaction quotient, right? So let's see what we've got here. We need a few things to figure out. We've got the temperature. It said it was 25 degrees, so that's kind of standard temperature. We'll need to figure out N, that's the number of electrons that are transferred. F's the Faraday constant. Like I said, Q is the reaction quotient, and then we'll also need the standard cell potential. So what we know about the standard cell potential, it is the standard reduction potential of the cathode minus the standard reduction potential of the anode. This is not in acidic or basic conditions, so that makes it easier. So SN2 plus in this case is getting reduced. There we go. So that's going to be my cathode. And then barium is getting oxidized. And so that will be my anode. Okay. So we will look those things up. Now remember, for our anode we actually look up the reverse reaction, but we don't change the sign of the standard reduction potential. So we've kind of answered a question here: how many electrons are being transferred? Well, there's only 1 tin in every case and 1 barium in the balanced equation, so N is just going to be 2. So there's another piece of the puzzle. So let's go into our Alex data section and see what well, let's find tin first. Tin 2 plus, yep, that one there, minus 0.138. And then barium 2 plus, it's going to be near the top, isn't it? Barium 2 plus, yep, that's fine, minus 2.912. Minus 2.912 volts, right? Okay, so E0 cell is my cathode, minus 0.138 volts, minus my anode, minus 2.912 volts. So it's going to be a very positive standard cell potential. So minus 0.138 minus 2.912. There we go, 2.774 volts. So this guy, it's a spontaneous reaction, right? So, and that's consistent with it being described as being a galvanic cell. Now, we're going to calculate the non-standard cell potential, and I'm expecting it to be bigger than the standard cell potential. So let's see what we get. All right, so what have we got? Our non-standard cell potential is equal to E naught cell minus RT on NF log Q. Okay. So what is Q? Q is the reaction quotient, right? Now we've got to be a little bit careful here because we've got some solids and they're not going to appear in our expression for Q. So E naught cell, or E cell, sorry, is equal to E naught cell 2.774 minus RT on NF, so 8.314, and our temperature was just 25 degrees Celsius or 298.15 Kelvin. On N, we said that N was 2, F was 96485, and then that is multiplied by log of Q. And so Q is products over reactants. So look at our balanced equation. You realize that the solids we don't include. So our products are just the barium ion concentration and the reactants are just our tin ion concentration. All right, and that's it. So we have those numbers, don't we, right? So our barium ion concentration was bigger. There we go, 2.64. We've done quite a bit, haven't we, before we got here. 2.64, and then our tin was like 7.73. Gonna put all of that into my calculator and see what we get. Okay, so 2.774 minus 8.314 times 298.15 divide parentheses 2 times 96485 times log 2.64 on 7.7. All right, there we go, 2.788. So E cell equals 2.788 volts. So I said it should be bigger than the standard reduction potential, and it is. All right, so so that's fine, 2.788. So happy about that one. All right, 2 more questions left. So if you want a little more information about how to tackle those problems, you just go Nernst equation, and you can. There's a pretty decent Wikipedia article about it. Okay, and here's the expression that we used. Okay, so one of the things that I just noticed there when I was searching that is that they had a Nernst equation calculator. So they probably have a little thing. There you go. So Nernst equation calculator. I don't know how good it is, but you could check that out and see if that was helpful. All right, number 6. Suppose 0.14 mole of electrons must be transported from one side of an electrochemical cell to another in 50 minutes. Calculate the size of electric current that must flow. This is using Faraday's constant, all right? So if I've got 0.14 mole of electrons, I know that I get 96,485 coulombs for every 1 mole of electrons. So that there would give me coulombs, and then I know if I divide coulombs by seconds, I get amperes, don't I? Right? So that's all I'm doing here is then that would give me coulombs divided by seconds, which is the same as amperes. So again, it's really just a dimensional analysis problem. So 0.14 mole of electrons, and I get 96,485 coulombs for every 1 mole of electrons. So this gives me the number of coulombs transferred, and then I'm going to divide that by the number of seconds. So it was 50 minutes, and there are 60 seconds in 1 minute. So that's going to give me coulombs per second. So it ends up being 4.50 coulombs per second, or another way of saying that is 4.50 amperes. So it's just really, again, dimensional analysis. You're probably pretty good at it at this point in time. All right, this is analyzing a diagram of a cell, right? So it's suppose a powerful battery. So that means it's a spontaneous reaction because it's a battery. It's discharging at this point. Oh no, they put a power supply in there. It's charging up. There we go. Suppose a powerful battery is connected between a pair of inert graphite electrodes. Okay, so the electrode is not getting oxidized or reduced. Dipped into a pot of molten aluminum oxide. So aluminum oxide has the formula Al2O3, and it's going to contain aluminum ions and oxide ions in the liquid state. So that's kind of cool. That's what's there. All right, so what's going to happen here is that one would expect that the aluminum ions, they're going to undergo reduction and make aluminum. Now the temperature is really high, so the aluminum oxide is going to, as an ionic compound, is going to melt at a much higher temperature than aluminum metal. So I know that the aluminum metal would be liquid. And then the oxide ions, what's going to happen to those is they're going to be reduced, and that's going to be 4 electrons in that case, all right? And now the oxygen even at room temperature is a gas, so under these conditions, where we're at the temperature that we can melt aluminum oxide, the oxygen is definitely going to be a gas, all right? Okay, so it says write a balanced equation for the half reaction that takes place at electrode A. So we have to decide are electrons being lost or gained at A. And you can see that electrons are being lost at A. So what are those two half reactions involves the loss of electrons? It's this one, right? So that is going to be A. That's where electrons are coming out of the system. Here are those electrons here, all right? And then it says write a balanced equation for the overall reaction. Well, we've just got to add together these two half equations, and we just got to make sure that everything balances. So 3 electrons are being gained up here, and 4 electrons are being lost there. So what I'm going to have to do is multiply this guy by 4 and that one by 3. So it would be something like this, or it would be exactly this: 4Al3 plus 12 electrons gives 4Al, and that's going to be liquid. And then this gets times by 3, so 6O2, or O2 minus, gives me 3O2 and 12 electrons. And then that's a gas, of course. Now reactants are both liquids because it said it was molten. And then when we add these together, they're going to cancel out. So we end up with 4Al3 plus liquid plus 6O2 minus liquid gives me 4Al liquid and 3O2, which would be a gas. Now there's only one bit that we missed, which is identifying what is the, so I should say that is B, what is the anode and what is the cathode. So it asks here, what is the cathode? Cathode is where reduction occurs, which is where electrons are gained. So it's got to be this guy. So that's the cathode. Okay, that's where electrons are gained, right? And that's consistent with our diagram as well. Electrons are moving into B. So what electron is the cathode? It's B. Right, a balanced half reaction that takes place at electrode A. We did that down there. And then this is write a balanced equation for the overall reaction. We had to add together the two half reactions. So that worked out pretty good. All right. Let's see where we're at.